So the point is that we first looked at some primary of some definite momentum, and it turns out this will be some integration over the minus direction momentum, or sorry, plus direction, for n particles. Right? So if these operators constructed out of n fields, then there will be n integrations over each momentum, and there will be some. This just comes from plugging in the free field expansion and there will be some function of all the momentum. And there's also this integration over the transverse rotations. But there's no method here. And this runs from minus infinity to infinity. And what happens is, so when we're trying to construct these basis operators, we try to normalize this inner product. And then, so you end up with some integral x1, z, this perpendicular direction is called y. And so you have two functions. So you can figure out which polynomials are orthogonal.
Okay.
So that's how in practice you get this thing. But like there's this overall divergence. It turns out that this wave function is just split up into.
Should I just start? Okay. All right. So I think we're ready to get started. So I've thrown up here just a basic overview of kind of what we discussed yesterday. So if you remember, I was outlining two basic sets of assumptions that give us sort of a starting point for thinking about dark matter and how we might search for it. So the first set of assumptions had to do with the distribution of dark matter in the galaxy. And the argument there was that we observe flat rotation curves. From that, we can infer that the dark matter density goes roughly as 1 over r squared. And then if we make this additional assumption of equilibrium, that the dark matter is in equilibrium, we could use Jean's theorem to relate the dark matter density to its velocity distribution, and we find that the velocity should be roughly Gaussian. And then the argument for the dark matter mass was that we start off with CMB data, which tells us what the observed dark matter abundance is today. And then if we assume the process of freeze out, that points us towards weak scale dark matter, so weak scale interaction cross-section, and a mass around 100 GeV. So these kind of give us our starting point. If you will, it's kind of like this is, if we're going to start looking under the lamppost for something, this is a reasonably good place to start. And then obviously if we don't end up finding this, then we're going to want to start thinking more broadly and trying to figure out how to go beyond the light from the lamppost. But considering that there's such a wide range of possibilities for what the dark matter particle would be, we do need some of these kind of motivating assumptions to kind of give us some starting points. So what I wanted to do today was have us all kind of get our hands dirty and think very much and think in quite some detail about some of these experiments. And hopefully the goal is just to build some intuition for how the theory links up with how you design the experiment and how how results from these experiments end up feeding back into what we think about the theory. So what I want to focus on specifically are direct detection experiments, because I think they provide a really nice way of seeing this interplay between theory and experiment. So the premise here, and I mentioned this briefly yesterday, was first outlined by Goodman and Witten in the 80s. And so the idea is to put, a chunk of detector, crystal, something, block of mass, really deep underground, and to just wait for some dark matter particle that's passing through Earth to knock into one of the nuclei in these detectors, And then the experimentalists would observe the nucleus jiggling, recoiling after this collision. And based on the properties of the energy of that recoil, they would then be able to infer what the mass of the dark matter was that hit the nucleus. So in an experiment like this, the quantity that we're interested in is the recoil rate, the differential recoil rate with respect E with the subscript r is going to be the recoil energy for the nucleus after the collision. So the differential recoil rate for a dark matter particle in one of the nuclei in these detectors just goes as the number density of dark matter particles streaming through the Earth, and then the velocity averaged differential cross-section. Oh, and times the number of target nuclei in your detector. So we have to do this averaging, right? Because precisely from what we determined yesterday, because we know that there's some distribution for the velocities of the dark matter particles. It's not just some stream of dark matter. So we need to do this average over all the possible velocities. So writing this out just more explicitly, this just becomes number of target nuclei, my dark matter density over dark matter mass. This is just the number density for the dark matter. And then I have an integral over velocities. So I have to put in my velocity distribution for the dark matter, and then I have my cross-section there. So this integral is going to go from some minimum value that the dark matter needs to cause the nucleus to scatter, and then some maximum value. What do you think actually sets the maximum value for the dark matter velocity? Can it be infinite? Yeah? Good. Okay, it can't be faster than c. That does set an upper bound. Okay. Can we do better than that? In the Milky Way? Oh, yeah. So that that's just going to create some small amount of spread in the velocities of the dark matter, though it's not that large. Yeah, I think about it. If you have your dark matter's in a halo, right? So think about it in terms of the galaxy. Yeah.
Another estimation would be that you can doctor.
Yes.
Otherwise, it would be away from the galaxy already.
Yeah. So the maximum velocity is essentially the escape velocity for the dark matter in the Milky Way halo. And how can we actually determine what this is? I mean, besides calculating, can we actually get a measurement on this? Yeah, so it'll be, this will be related to the rotation speed, because then that'll give us some estimate on the enclosed mass that's there. And then we can also verify anything that we determine from this using looking for the fastest stars in the Milky Way. So people have gone out and actually just done measurement, look at what's the velocity of the fastest stars we can actually observe, and use that as a way of just, that's essentially a tracer for what the maximum velocity allowed for the dark matter particles would be. And so it's somewhere in the range from 550 to 650 kilometers per second. So
this is basically the Maxwellian can't really can't be any closer because the scale will always be at too high a velocity.
yeah. Okay, so that sets the maximum value for the integration here. The minimum value gets set just by basic kinematics. Okay? Actually, you know what? Let me just pull this up. So the average velocity for dark matter that's in our neighborhood is going to be similar to the velocity of the sun, which is roughly 220 kilometers a second, right? So dark matter is actually not, I mean, we can consider it just being non-relativistic. So when we determine things like minimum velocity or work out any kinematics for these kinds of scattering, it literally is like two colliding balls that you've done in, freshman physics. So for example, in this case, the initial, thing is I've got my dark matter particle coming in and my nucleus that's just sitting there. It's at rest because it's in the detector. And then the final configuration is my dark matter comes, my nucleus comes recoiling out, and here's my dark matter particle. So I'm just going to label these momenta. Is this what oh, no. The recoil of the dark matter is not something we'd ever be able to measure because we're not going to see it recoiling off, right? It's neutral. It's going to bounce off. We're not going to notice that. The only thing we can hope to measure is this recoil momentum here. So why don't you take a minute or two and then just write down the four the four vectors here, but specifically what I want you to find is what the momentum transfer is in this process. So let's call that Q bar, and that's going to be P bar 3 minus P bar 1, or so specifically, I want you to relate the momentum transfer Q to the recoil energy of the nucleus. So maybe just take a couple minutes to kind of set that up, and then we'll go through it on the board. Oh, yeah, you could do it in terms of the scattering angle. We'll call that theta. Okay, so probably just had some time to kind of get that set up, but so what I was getting at is just that the momentum transfer squared is just going to be twice the mass of the nucleus times the recoil energy. And that if I wanted to write out a 4 vector associated with this momentum transfer, right, that it would be Q is just going to be the recoil energy, and then times the cosine theta. So this is all, just, non-relativistic kinematics, sine theta and 0. So the point is mainly that the nucleus initially just has 0 velocity, so that's what allows you to just automatically write down that the recoil energy is related to the momentum transfer. So once you just set this down, and then it's just a bit of algebra, what you end up finding is that the minimum scattering velocity depends on a variety of things, including the dark matter mass and the mass of the nucleus, which makes sense. So this is mass of the nucleus, this is its recoil energy. This part in the denominator here is just the reduced mass of the nucleus and dark matter. And what I've included here is a mass splitting in the event that the scattering is not actually elastic. So you can have, for example, a case where a dark matter particle might come in and it has some initial mass m chi, and then after scattering it might get an upkick such that it goes to an excited state that's very, 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 very close to the initial state, and in this final particle here can then have mass m chi plus delta. So this is the minimum velocity that the incoming dark matter particle has to have in order to create a nuclear scatter with recoil energy ER. Okay? So a few things. For now, we'll just take delta equals 0, so the pure elastic scattering limit. So minimum velocity goes up as the mass of the nucleus goes up, right? That makes sense intuitively, right? If I have a much heavier nucleus, I'm going to need a dark matter particle coming in at much higher velocity in order to get it moving. And similarly, minimum velocity goes down as the dark matter mass goes up. So if I have a really massive dark matter particle coming in, it could be coming in more slowly and still kick the nucleus with the same amount of energy. So what I want to do now is just kind of take a moment to build up some intuition for how you would actually choose an appropriate target for a given dark matter that you're interested in. So specifically, let's come back to the rate expression. It's going to be proportional. I'm just going to, let's forget about the constants out in front because that's not going to be terribly relevant. So it's going to be proportional to f of v and v if d sigma der is proportional to 1 over velocity squared. And we'll come back to that later. So this is essentially then just an integral over velocity times the f of v. So if we take the velocity distribution to be Gaussian, right, then the integrand here just looks like something like that, where this is velocity down here. So when I'm doing this integration, I'm going to be integrating from some minimum velocity here up to the escape velocity, wherever that is. It's going to be somewhere out here on this tail. So for different minimum velocities, I'm actually doing integrations over different parts of this curve. So I'm sampling over different velocities of the incoming dark matter. So if my minimum velocity was much lower, I'd actually be doing the integration over a much larger part of this curve and sampling the velocities, sampling almost over all the velocities of the incoming dark matter, as opposed to having a higher minimum velocity. So this would be high Vmin and low Vmin. So if, for example, I was plotting this for the same target, so the same nuclear mass, which one of these, the left or the right, would correspond to a lighter dark matter particle? Left and right. All right. Reasoning. So, reasoning for left? Okay, with right, whoever yelled out right, what's your counter argument? Yeah, so this one is for heavier or light dark matter? Oh, so then I think you guys are saying the same thing. Yeah. Okay, good. Yeah. So this one here would correspond to the heavy dark matter case, and this one here would correspond to the light dark matter case. Oh, it's in the reduced mass. Yeah. So this tells you that for the same target mass, you'd expect to get a larger rate for a heavier dark matter particle than you would for the light dark matter particle. And also that the light dark matter particle is going to be very sensitive to any deviations, because you're integrating over smaller regions, so it's going to be really sensitive to whether or not you're getting your assumption about this velocity distribution right. Okay, so now you should have enough intuition that you can serve as a consultant to an experimental collaboration. And they're going to want to, one collaboration is going to want to try to discover, their goal is to discover a 10 GeV dark matter particle, because, some theorists thinks that that's exactly the mass that you'd want to search for. So as the consultant, you need to tell them whether or not should they use a germanium target or a xenon target. And then similarly, their competing experiment says, oh no, dark matter is clearly not at 10 GeV. We're going to discover it at 100 GeV. But they still pay you for your consulting abilities. So you should tell them whether or not they should use germanium or xenon. Oh, okay. Germanium's going to be lighter than xenon. That's about all you need to know. So does anybody have an argument that they'd be willing to get paid for? Yes. So you would actually want the germanium target for both, But would you? Yeah. So how important is it? Is it more important that you choose germanium for this one or for this one? For the lighter one. Yeah.
So I mean, it looks like we really need to write out what the reduced mass is to answer this question, right?
Yeah, to answer it exactly, you'd want
an interesting result, which seems like it's mn plus n pi root mn. Kind of, I mean, it is right. You get some kind of funny where it depends on where you are on the curve, whether you want the mn larger or less.
Yeah, no, that's true. Yeah. And so so in the case where it's xenon, the mass of a xenon nucleus is really similar to actually 100 GeV. So these two would be similar in mass, and you kind of hit a sweet spot there with the sensitivity. But you're not too far off either with using germanium. Using germanium is much more crucial if you want to go to the lighter dark matter masses, though, because because then the disparity between the mass of the xenon and the 10 GeV is much greater. So, I mean, this is essentially just, I have a small ping pong ball hitting a bowling ball, and so that's not going to cause the bowling ball to move. Yeah?
So, a lot of the experiments that
Exactly, yeah. So they're using xenon, because there's a couple reasons. One is because they're targeting this mass range. So xenon provides, because the mass is about the same as 100 GeV, provides a really nice target for that. And then also because, just for experimental reasons, if you put a tub of xenon, if you use a tub of xenon, it self-shields, and so let me draw it. So here's my tub of xenon. I can choose like just this inner region here for scattering, and it's a nice background-free type environment. So there's nice reasons experimentally why you'd want to actually choose xenon. But there are like CDMS's germanium. Yeah.
Sorry, I didn't understand why
So if you look at the minimum scattering velocity, right, the dependence on the dark matter mass is coming from the reduced mass that's there. So we can actually just write this out explicitly. So Vmin is going to go as, let's just take the first term. So that'll be square root of mn E recoil over 2 times reduced mass squared, right? And then I can write out the reduced mass explicitly. So that would give me the following. Good. And then I get a cancellation here between the nucleus, the nuclear mass, top to bottom. So what this ends up becoming as, let's see, I get mass of the nucleus plus mass of dark matter squared, E recoil, over twice mass of nucleus, mass of dark matter squared. Right? So there's, if, for example, in the limit where dark matter mass is really, really light, then this will reduce down differently to the case where the mass of the nucleus and the mass of the dark matter are roughly the same. Does that make sense? Okay. Okay, can I hide this board? No. Okay, so having built some intuition for that, what an experimentalist will actually, once you've told them what kind of target to use, they'll go out and actually do this measurement. And what will they see? What actually is the recoil spectrum that they would observe? So if we're running under the assumption that the velocity distribution is just a Maxwell-Boltzmann, then we get this simple scenario where this is just an integral over, it's a simple integral to solve. And very roughly, it's just a falling exponential in recoil energy. So if an experimental collaboration is observing a signal and we're to plot the rate of scattering as a function of the recoil energy for the nucleus, they would see it as a falling exponential. So this is what happens in the case where I have elastic scattering of the dark matter off the nucleus. Can you sketch out what would be different in the case where it's inelastic scattering between the dark matter and the nucleus? Thoughts? Yeah, so what you're getting at, I think, right, is the minimum velocity is going to go up or down? Up? Yeah, so the minimum velocity to scatter is going to go up, because now delta isn't 0 anymore. So that means that when I do this integral, it's going to look the same at high energy, but now the cutoff here is much higher. So I'm not going to get any scattering at low energy, because a low energy scatter just wouldn't be enough to be able to upkick my dark matter to the excited state. So this is a way that, depending on what would be observed in terms of the differential rate by an experiment, it would actually give us an immediate link back towards learning something about the what's actually in the dark matter sector, right? Because if they were to observe this over this, then that might tell us that there's actually more than one particle in the dark matter sector. And so you might have, a spectrum that looks more like, here's my first dark matter particle, and maybe there's some little excited state that's very, very close to it. such that you get this inelastic scattering. And so in that case, you'd see a differential rate that looks like that. Any question on this before I move on? No? Okay. So what I wanted to do now is to actually describe in some more detail how you actually determine what this differential scattering rate is for the dark matter in the nucleus, and how that's related to the non-relativistic operators for that interaction. Now, the way I'm going to outline this is actually a bit different than the way it's usually outlined in the literature. And that's the reason for that is that typically what's done is to make just two standard sets of assumptions about what the relativistic operators are for the dark matter scattering, where those two relativistic operators are the ones that typically fall out of supersymmetry SUSY-type models. The approach that I'm going to take is one that's a bit more general, which you could use for any type of model. So the steps that we're going to follow are, for any general interaction, the first step will be to determine the effective potential of the interaction in position space. Then the second step will be to determine the non-relativistic matrix element that corresponds to this effective potential. And oops. The way you can relate the two is through the first order Born approximation. So my non-relativistic matrix element, which is a function of, now we're going to get Q is used for more than one thing. So this is position, and velocity is following just the Fourier transform of the effective potential. So this is just the Born approximation. And then the last step is to relate the non-relativistic matrix element to the differential cross-section. And that just comes from the following. So again, this is just essentially boils down to using non-relativistic scattering to explain the interactions of the dark matter with the nucleus. Oh, yeah, sorry. Good point. Yeah, this is just the spin average. So this is the number of spin states for the nucleus and the number of spin states for the dark matter. Good. So J is the nuclear spin, and S with the subscript chi is the dark matter spin. So to illustrate this explicitly, let's consider the case where our effective Lagrangian is the following. So I'm starting, I mean, this is my relativistic interaction between the dark matter and the quarks. My gammas here can be, you know, this is my notation. Here we go. I mean, they could be unity. They could be a set of gamma matrices, combos of gamma matrices, etc. And this factor out here is meant to, it's sort of shorthand for the propagator. So in the limit where I have a heavy mediator between the dark matter and the nucleus, then this is what I get. And for a light mediator, I have 1 over momentum transfer squared. Yep. Yeah. Yeah. Yeah, no, it's totally right. So if dark matter only interacted gravitationally with baryons, these experiments guaranteed would see nothing. Yeah. So we would, we have to have some kind of interaction, and the easiest way of kind of parametrizing all the possibilities is to use these effective operators. And so essentially what we're looking for are, dark matter, and then there's some mediator, which I'm calling phi, and here's my quarks in my nucleus. And so when I write down my effective operator like this, it's just ways of parametrizing different circumstances here. So I could either have a heavy mediator where this is essentially just a contact interaction, or I can have some long-range force if it's a light mediator. So as a simple place to start, I'm just going to work out the example when these gammas are just unity. So in that case, I have an effective operator. Let's also just do the heavy mediator case first. So then my effective operator looks something like this. Just chi bar chi and q bar q. So now we want to go back to our list up here and just follow it step by step. So you're given essentially this is the relativistic operator, and now we need to figure out what the non-relativistic scattering cross-section is. So the first step is to determine the effective potential for the scattering interaction, making the assumption that the dark matter particles on the nuclei are non-relativistic. And so one way to do this is to start off as if we're evaluating this in the relativistic formalism. So writing down our spinors. So these are just the spinors for the incoming and outgoing dark matter and quarks. And then next, what we'd want to do is just substitute in what the spinors are in the non-relativistic limit. Okay? So in the non-relativistic, oh, now I'm going to put that too big. do this here. So in the non-relativistic limit, I can write down the spinner as follows. Where the C's are just the two-component spinners, right? So ordinarily, if you write out the spinner in its full, write it out completely, it's going to have some dependence on the momentum. But what I've done here is just sort of expanded it out in the small momentum limit. And so we can then substitute in that spinner here and get what the matrix element is in this non-relativistic limit. And it's essentially just a bunch of delta functions between the spins and then products of the nuclei mass and the dark matter mass. So at this stage, I mean quarks. Oh yeah. So your question is what's this mass? Yeah. So technically at this point, I should do that. Yeah, it does stay together, and I was going to make a note. I'm going to mention later how you actually handle that. So I was kind of jumping ahead a few steps by putting the n there, but yeah. Okay, so this gives us our non-relativistic matrix element. And once we have this, we can very easily determine what the effective potential is. Let's see if maybe I should go wash some boards. Okay, so, wow, everything's like rainy, drippy. Okay, so at the bottom of the board on the right, we have the non-relativistic matrix element. From that, we can relate it to the effective potential. And so see what we've got here. These masses are just coming from a relativistic normalization. So they kind of go away when we put them in the non-relativistic potential. These are just delta functions in spin. And the only thing we're left with is this mass of the mediator. So the effective potential in this case has no dependence on the momentum transfer. It's just a constant, 1 over mass squared of the mediator. So this is step 1 in our to-do list. Step 2 is to relate this. So step 2 is just to get this into the, oh wait, no, actually no. That's step step 1 is to get this just in terms of the position coordinates. So I just do the Fourier transform of this, which is pretty straightforward because I'm just putting in a constant. And what I get out is some constant that I will label with a lowercase h for heavy mediator case, and a delta function in position. So this is just a statement that when I have the heavy mediator case, the interaction is just a contact interaction between the dark matter and the quarks. As an example of how this would be different in the case of the light mediator, so I'll put this in parentheses, this is heavy mediator. If I had a light mediator, things would end up changing because my effective potential now doesn't have just a mass here. It also has, it's going to have a 1 over q squared. So this is going to depend on the momentum transfer. So in the light mediator case, in this one, the potential is just the same exact thing we got before. Except that now there's actually this factor of potential in there, so that when I write down the effective potential, it's now proportional to 1 over q squared. And when I determine what the potential energy is, the dependence on position, it's the same integral, except this is now 1 over q squared. So slightly more complicated, but still doable. And what I get in this case is that the effective potential is proportional to some constant that I'm going to call L1 times a factor of 1 over r. So this is just a statement that when I have a light mediator that's causing this interaction between the dark matter and the nucleus, then I have, it's a long-range force. So one thing to really note so far is that the expressions that we're getting for these effective interactions have no dependence on either the spin of the dark matter or the spin of the nucleus. That is something that's very particular to the assumptions that we made about the initial effective Lagrangian. So I could have started off with an effective interaction that had gamma 5s or something in here, and that would have ended up giving me factors of spin in this effective potential. Yes? Doesn't have to be fermion. Yeah, good. Yeah, no, it doesn't have to be fermion, which is why, yeah, I mean, it could be scalar, it could be vector. Yeah, and writing it out in terms of these effective potential kind of emphasizes the fact that it could be, you know, you can write down different operators if you're assuming that it's scalar. Okay, so once we have our effective potential, then we're pretty much all in gear to finish going through our steps there and determine what the non-relativistic scattering cross-section is. And so I'm just going to write out the final answer. For these two cases. So in the scenario where I have a heavy mediator, the effective potential is going to look like this. So these are just the constants that go out in front. And then this H1 is coming from the effective potential. So a few things of note here. One is before, I think it's probably still on the middle board, I made a note that the differential cross-section goes as 1 over v squared. So that's coming from this. And the other important aspect of this is that the dependence on the recoil energy is actually different depending on whether or not I assume that it's a heavy mediator or a light mediator in each case. So based off of what we did on the middle board, maybe just take a minute and sketch out how the differential rate would look different if I have a heavy mediator or a light mediator, and which case should be easier to discover. Are there any thoughts? Maybe I should start off with this. So what should I draw for the heavy mediator case? Yeah, same thing as the middle, right? So that's just falling exponential. That's the heavy. And relative to this, how is this one going to look different? Should it fall down more steeply or less steeply? I heard mumblings. With confidence. More? More, yeah. Yeah, so it should drop off more steeply because of the factor of 1 over recoil energy squared. So the light mediator would look something more like this. And any thoughts on which one would be easier to discover? Can you just directly? What do you mean? Oh, in other ways, yeah. Yeah. But I meant just this way. Yeah. I actually probably drew this not well. Huh? Yeah. Yeah. So in general, the heavier one would probably be easier to find just because it tends to give you more high energy recoils for the nucleus, as opposed to the light one, which gives you more low energy recoils. And so the higher the energy of the recoil, the easier it would be to discover it, just from a purely like measurement standpoint. Okay, So I did just want to make a few side notes. The first is that I kind of glossed over this, although it was brought up. It's that the nuclei, we can't consider the nuclei as being point particles, because essentially the momentum transfers that we're talking about here are on the order of the size of the nucleus. So the dark matter should actually be able to resolve the whole size of the nucleus. And so one would technically needs to do this carefully, and you end up getting things that look like matrix elements for the nucleus before and after the momentum transfer, and then in here you end up with your factors of the quarks and things like that. So these kinds of matrix elements end up giving you additional form factors associated with the size of the nucleus, the interaction. And then the final point, which I was kind of hinting at before, is that this illustration was done purely for this effect, this operator that's chi bar chi, q bar q. This is what will often be shown in the literature and referred to as spin-independent interactions, which is why I kind of did it out in full here, because it's the example that shows up everywhere. But I could also, I could repeat the whole same procedure with any other set of operators. If I did, for example, if I put in a gamma 5, gamma mu between both of these, I'd get a spin-dependent interaction, and then I could do all sorts of permutations off of this.
Is there big qualitative differences between spin-independent and independent?
Yeah.
Is that something you can get to, or?
I can. Yeah. No, there actually is a very big qualitative difference. Yeah. So where should I put this? Let's see. So in the spin, when I don't depend, spin-independent, when I don't depend on the spin, when the interaction does not depend on the spin of the nuclei, then that means that the dark matter particle interaction is pretty much the same regardless of which nucleon I scatter off of. So when I sum over all of the contributions from each of the different nucleons, it sums coherently. And the differential cross-section in this case, the total differential rate ends up being proportional to the atomic number squared. And that's just coming from the fact that I can add up the contributions from each of the nucleons individually, and that it all sums up together.
Is that somehow contained in what you've done already, or is that
that's going to fall out of this part, which I didn't do very much, but it falls out from there. Yeah. If I actually do depend on the spin of each nucleon, then I lose this coherence, because now the scattering rate is going to be different depending on which nucleon I scatter off of, because it's going to depend on their spins. And so in that case, the differential rate is not proportional to a squared. So generally speaking, when you don't depend on the spins of the nucleon, the scattering rate is much larger, so it's easier to discover. In the case where you do depend on the spins, you lose the coherence, so you lose this boost in these atomic numbers are order 100, right? So you gain a lot by having this coherence in the spin-independent case. So limits for spin-independent cross-section tend to be much stronger than limits for the spin-dependent case, just because the predicted rates are larger. So I wanted to just kind of sketch out what the current limits are as of now. There's a ton of different experiments. And if I actually sort of showed the plot on a transparency, there would be a bunch of lines and it would look very confusing. But I'm just going to kind of reduce it down to the best ones. Well, not that the other ones are bad, but the ones that are giving the most relevant limits as of now. So this is just a schematic drawing, but just to kind of walk you through what these limits, if you see these like in a talk, this is what people will tend to show. So the limits tend to be shown on plots where the x-axis is the mass of the dark matter, and the y-axis is the interaction cross-section between the WIMP and the nucleus. And usually it's shown in terms of centimeters squared. So right now, the strongest limit, let's do this. The strongest limits are coming from the xenon experiments. So I'm going to just, and in particular from lux. And the sensitivity right now for lux is roughly at 10 to the minus 45 centimeters squared. So that's the best that they're able to do. That number is important. It's actually very important for one reason. So sometimes when people show these plots, they also overplot it with some blob that looks like this, that they then say is SUSY. And then if you look at these plots as a function of time, the blob moves. So as a function of time, it's actually really funny if you overlay it, like it just shifts. As the limits keep getting better, it shifts, because what goes into that blob is like a full Bayesian analysis with priors for including all possible limits. So over time, the limits get better, and the blob just shifts down because we haven't seen SUSY yet. So really, that's not the right way of thinking about it. The best way to think about it is in terms of the cross-sections that you're probing. And so I want to explain why this 10 to the minus 45 is special. And the reason it's special is because that's right where we're becoming sensitive to dark matter interaction via exchange of a Higgs. So if I had dark matter interaction via a Z boson, the cross-section is roughly 10 to the minus 39, and that was excluded a long time ago. The only other weak interaction that we still have left is via the Higgs, and that sweet spot is here. So in particular, like you could just kind of back of the envelope it. This scattering cross-section is proportional to these two coupling constants. And then I get factor of mass of the Higgs to the fourth, the denominator, just coming from the propagator, and then the reduced mass of the dark matter and the nucleus. And if you just put in the numbers for the Higgs mass and a xenon target, you find that this is roughly 7 times 10 to the minus 44 times the interaction coupling between the dark matter and the Higgs, centimeters squared. So there's wiggle room here because you obviously depend on what this coupling strength is, but roughly speaking, there's this region that kind of goes from, there's kind of this wide band region here that's really, really interesting because it's right where you'd expect the Higgs to be mediating it.
Sorry, but going back to the you made an assumption that the dark matter particle couples.
Yes, yeah, this is for spin independent. Yeah.
So the assumption is 10 to the minus 45 is the assumption that God knows why dark matter particle couples in a spin independent the Higgs, and that's the portal to.
Yes. Yeah.
And that's where it is. And so when the limits drop below that, we're in big trouble.
We're in trouble for several different reasons. I mean, you then have to start getting more creative. This is a nice simple picture, right? So if the Higgs were the mediator and it was a spin independent interaction, beautiful, like simple. We've discovered the Higgs. Now we know it's a portal to dark matter. It sits right here. If that turns out to not be the case, then we know that the situation is much more complicated. It might be that you still have Higgs interaction, but maybe you have additional particles that are canceling out, like that are also contributing, and so the total cross-section when you add in the two amplitudes cancel out. So the situation becomes more complicated, yes. Yeah?
So if you're assuming some Higgs interaction, is that also how dark matter is getting its mass?
Well, yeah, I mean, this is making the assumption that it is getting some mass from the Higgs. Yeah, these types of models are called Higgs portal models. Yeah, and there's other ways that you could set constraints on these, and I'll talk about them tomorrow. So we can get constraints on these, for example, from branching fractions of the Higgs at the LHC. So this is one case where you can start seeing the complementarity between all the different experiments. Do I still have a few minutes?
Yeah, 5 minutes.
Oh, okay, perfect. Okay, so this is Lux. This is a nice sweet spot. If I keep moving down in cross-section, so up here, there's no other standard model background that's contributing. If I go down in cross-section and I get down to, well, I'm going to sketch it in, and I want you guys to think what possible background is going to be kicking in right where I'm sketching this line. So below this line, there's some standard model process that starts contributing. Yeah, so below this way, then I get coherent neutrino scattering off the nuclei. And the experiments no longer become background free. And the shape of this is actually determined from the fact that this actually should go up. Depends on which neutrinos you're scattering off of. But yeah, so if these experiments start becoming so sensitive that they get below this line, then they're actually going to start measuring neutrino scattering. So actually then they become multi-purpose experiments. But and I mean, I don't think it will stop the dark matter exploration, because we're just going to have to figure out a way of distinguishing the dark matter signal from the neutrino signal, but it will become harder. And it won't be a situation where they can kind of keep doubling the size of the experiment and it will automatically double their exposure. It's going to be a lot harder work to keep pushing down below that region. Currently, the next round, so this Lux experiment was maybe 300 kilograms of xenon. There's a bunch of 1-ton experiments, and they're going to start pushing down roughly here-ish. So like xenon 1 ton. These are the ones that are currently being built now. They're going to push down to like 10 to the minus 47 or so. And so that's something to kind of keep an eye out for, because data from that will probably start coming out into this year, next year. And then I'm not going to draw them all, but as soon as you start getting down to this region, if you were to look at these actual plots, there's all these blobs of detections, most of which are not very viable, I think, is the conclusion at this point. But there are some experiments that have claimed to see signals, and there are clearly in tension with experiments that have not observed the signal, so they haven't been reproduced. And just one last note, which is that there's this whole region here, which current experiments just aren't that sensitive to. You can see most of their sensitivity collapses below 10 GeV. So there's some experiments that are being specifically designed to move this way. One of those projects to have limits that look something like this. These are CDMS. Based on our conversation before, which target are they using? Germanium. Yep, germanium, and then these are the xenon targets. So the next round of these CDMS experiments are going to push here. And I'll leave you with one final question that you can just kind of mull over, which is all of these experiments are focusing on scattering off of the nuclei in detectors. So as we drive the mass of the dark matter lower and lower and lower and lower and lower, so let's say I'm interested in MeV scale dark matter, I'm not going to be able to detect it at all with scattering off of nuclei, because that's literally a ping pong ball being hit at a bowling ball, right? How would I need to change these kinds of experiments such that I can detect things like MeV scale dark matter. So that's something that people are discussing a lot right now. I'll just give you a hint, and then you can think about it when you're walking off to lunch. There's other things in atoms that are not nuclei. And then you could start thinking about whether or not you'd want to do this in semiconductors versus atomic detectors versus superconducting detectors, et cetera, et cetera. Totally open ground right now for this. It's kind of like the next frontier for these kinds of experiments. All right, so I think that's lunchtime then, right? Yep. Yep.
Are they mostly from the sun or all from the sun?
Yeah, I think actually most of them are from the sun. Let's see, I wrote them down here. Oh, no, so these ones are sun. There's some atmospheric ones that kick in here. Yeah, yeah.
So you can tell where they're from.
Yeah, just because that's essentially everything that's shaping this is coming from all the different contributions. Yeah. Yeah. Yeah.
These blocks that you have written there for the maximum, do I have to understand that there's like some of this WIMP with like a 10 GeV mass? Is that the reading?
Oh no. So the way to read it is that everything above the line is excluded.
I see.
So they can exclude a 100 GeV dark matter with cross sections smaller than or larger than 10 to the minus 45, right? And they can't exclude anything here.
So what would be the perfect plot here to tell you what the mass of the particle is? Is there such a thing here?
What do you mean, if they were to discover it? Or, I mean, this limit, so when they draw lines, it's a limit because they haven't observed anything. If they do observe something, then it shows up as a blob, because that's the mass of the dark matter in the cross-section that would be consistent with having seen a signal. Yeah, great.
So just this is a silly question. So
Yeah.
Besides lowering the mass of the target, why would you need to target something else for detect? So if you want to detect dark matter at the MeV level?
Oh, if you wanted to go this way?
Yeah. So why would you simply just lowering the mass of the target?
Oh, yeah, because after a certain point, you can't, the smallest nuclei you could use would be hydrogen, right? But you can't actually, it's not feasible to build a target with hydrogen. So I mean, that's kind of like the fundamental limit, right? So what are the reasonable targets that you can build with nuclei?
Right.
Yeah, and some people are thinking about whether or not they could do it with helium. But yeah, after a certain point, you kind of hit a limit. Like the germanium and silicon are kind of the best options and the lightest ones that people have tried so far.
I see.
Yeah, and so that's why then people are starting to think about using.
Would you talk about how they are possibly going to use semiconductor or superconductor, like you were saying before? Or are you going to talk about that?
Oh, well, I mean, I could talk to you about it, but yeah, I wasn't planning on talking about it tomorrow.
Okay.
But yeah.
Okay.
So the idea for the semiconductor case is, so you would scatter off of the electron, and you would excite it. So if, let's say, you were scattering off, did you need this? Yeah. So let's say you were scattering off of